Alrighty, on to lesson 1.1.4, using data to solve problems. This is a preview of what we're going to be doing when we get to chapter 7, when we're going to be doing some data analysis, and we're going to be integrating our, not really statistics, but it's kind of like statistics into our problem solving. And today, we get to do what would be like a hands-on kind of active activity if you were in class to participate in it. But luckily I saved data from previous years, so we're going to be able to make this work. We're not going to, this is one where you're not going to probably have to write down too much today. Just more pay attention to what's going on. And when we get to the scatter plot, it might be a good idea for you to copy down some of it as well as the table, if not all of it, just to kind of get a general idea of what it looks like with what we're doing here. Okay, so computing batting averages, performing scientific experiments, and polling people during elections are just a few examples of how data can provide useful information when it is collected and analyzed. In this lesson, you will be collecting and organizing data to determine the potential danger of riding a roller coaster. Okay, so let's set the stage here. Have you heard about Newton's Revenge, the new roller coaster? It is so big, fast, and scary that rumors about it are already spreading. Some people are worried about the tunnel that thrills riders with its low ceiling. Now you can see right there, here's the people riding in. You know how people like to raise their hand, but look how low that tunnel is. I would be scared by that too, especially when you consider how fast these roller coasters get. So the closest the ceiling of the tunnel ever comes to the seat of the roller coaster is 200 centimeters. So remember, here's the seat, not from the bottom, but from the seat. When you measure straight up vertically, the highest point, well, I should say, not the highest point, but yeah, I guess the highest point of the tunnel, the top of the tunnel, is 200 centimeters from where they are sitting. Although no accidents have been reported, it is said that very tall riders have stopped riding the roller coaster. So our task is to see with students in our class if we can figure out, if we can solve this problem for this amusement park as to whether or not this is truly a dangerous ride or whether or not it should be safe based on data that we collect from people in class. So what we had students do is we would have students measure themselves twice. First, they would stand against the wall, and I have measuring tapes up on the walls, and a partner would measure how tall they were in centimeters. Then they would sit on the floor and reach up, as if the floor is like the seat of the chair, and they would measure their reach. See how that person is reaching up? So how far is it from the floor where they're sitting, that would be like their seat, all the way up to their fingertips. And then we would record that data as well. So I'm going to go ahead and skip this part right there, and let's just jump into it. So this is what we do: is we collect the data. We created a 3-part table where students would have their names written on the left, and then after measuring each other, they would come in and write their heights in centimeters and their reaches in centimeters on the table. And this is what the data looks like. Okay, so I took 20 students from a previous year, and this is the exact number that they recorded for their reach and for their height. And I plotted each one of these as if they were ordered pairs. So this is like we're going to make the height the X, and the reach will be the Y. So we come out here, and we set up a coordinate grid, but we're only going to use the first quadrant, okay? And so let's come back to this in a second and answer some questions here. For problem number 26, it says, use the class graph to answer the questions below. Are there any dots that you think show human error? That is, are there any dots that appear to be graphed incorrectly or that someone may have measured incorrectly? So when we take a look at all those dots, I'll tell you, what you're looking for in a situation like this is to see if you can get what's called a line of best fit. So a line of best fit goes through the data and it kind of evenly splits, kind of like a median, all of the points there. Now, because it's a scatter plot and everybody is different, not everybody's going to be the same height, not everyone's going to have the same reach, and some people are taller with slightly shorter arms, some people are shorter with slightly longer arms. No two people are built exactly the same, so that's why you're not getting everything perfectly on this line. Now, if you had one person that was super short but had really, really long arms, a really long reach, this would be considered an outlier because it is so far away from the rest of the data. You could also have someone who was like a Tyrannosaurus Rex, who was really, really tall, had little tiny arms. That's never happened. No Tyrannosaurus Rexes in my classes ever. So that would be an indication of an outlier if you had a point that was really far away from our line of best fit. So I would say, based on the measurements that students did this particular year, that there doesn't appear to be any outlier. If there was, it could be human error. I would probably, if I saw something that was way off, I would probably have students measure again just to make sure. But in this case, we don't have any outliers, so we don't have to worry about that. Is a person's reach related to his or her height? That is, what seems to be true about the reach of the taller people? Well, this is where you get into the line of best fit. It looks to be that there's a trend here. The taller the person is, the longer their reach is, right? We don't have too many situations where, well, I guess, no, we don't have any situations where you've got outliers out here or out here. But you know, if you started having these like all over the place, then you wouldn't be able to draw any conclusions. If you had a bunch of points here and then they were descending in this direction, then that would imply that the taller you are, the shorter your reach is, which is not this situation at all. This is definitely saying there is a correlation between a person's height and their reach. The taller they are, the longer their arms tend to be, so the longer their reach is. Since a person's reach depends on his or her height, the reach is called the dependent variable. That's our X variable. No, it's not. That's our Y variable. And our independent variable is the height. So if we examine the class graph for this particular one, which axis has the independent data represented? So the height is the independent data, and we're trying to see how that affects the reach, which is the dependent. So which axis is this horizontal axis? That's the X-axis, correct? So we can say that the height should go on the X-axis and the reach would go on the Y-axis. So there appears to be a trend for this data, right? And how can you tell if there's a trend to the data? If it appears as if there is a straight line, or it doesn't even have to really be straight, it can be a slightly curving line, but that's the key, is does it appear to form a line? And the closer it gets to forming a perfect line, the stronger the association between the independent and the dependent variable. If you start getting more points like here and here and here and here, and they're really spread out, then we would say that's a weaker kind of an association. But it still tends to trend in this direction, right? You're still, even with these spread out a little bit more, you're still seeing that the taller you are, the longer your reach is. So that's one of our goals here, is to always look to see on a scatter plot if you can see a straight line, and then how close are all the points to that line. When you get into high school in your freshman year, you'll do more work with this. You'll actually measure the distance of these points to your line of best fit and use those calculations in certain ways. So, is there a trend to this data? I would say yes, there's absolutely a trend to the data. There's a pretty clear line of best fit. All right, now, nobody's complaining about my graph that we created, but in this particular CPM classroom, we have some complaining going on. Jorge is confused about how the teacher decided to set up the graph. He asks, why is it a first quadrant graph instead of a 4-quadrant graph? Now, remember the difference between the two. A 4-quadrant graph looks like this. A first quadrant graph, remember the first quadrant is right there. This is the second quadrant. This is the third quadrant of our coordinate grid, and this is the fourth. We don't need any of the negative values because nobody's measuring a negative height or a negative reach for this particular activity. So what's the point of having all of these? Let's just stick to an L-shaped graph that only has the positives. So the answer for Jorge is all the measurements are positive numbers, so you don't need any other quadrant besides the first quadrant. That's why you see so many graphs that are L-shaped graphs, because if you're only dealing with positive numbers, there's no reason to use the rest of it. Lauren is annoyed, okay, with the x-axis. Why didn't the teacher just use the numbers from the table? Why count by 20s? Okay, well, the numbers in the table, the x-axis, what is the lowest one here? 150? And the highest one is 181. So you wouldn't have much of a spread for your data there. It would really be congested. You'd have this really small graph if you only included those numbers. So you kind of want to spread it out a little bit. And I think I counted, while I enumerated by 20s, I actually counted by 10s on there, not counting by 20s. I wanted to spread it out even more, but you got to be careful about, remember how you scale your axes. We did an activity in 7th grade where if you didn't stretch it out enough, all the data points would be scrunched together and it'd be really hard to analyze the data. So I think Lauren just needs to get over it. Counting by 20s makes the graph a little reasonable size for everybody to see, and it's spaced out enough. And then who's this person? Hosea thinks that the graph is too big. The dots are all mashed together. Why did the teacher begin with both the x and the y-axis at 0? Well, as you can see, I chose not to do that. Knowing, and he's exactly right, I agree with him. Nobody is going to be like 20 centimeters tall and have a reach of only like 18 centimeters. The shortest person was 150, and I've got 2 shorter people right there, but I'll reveal who those are in a second. But most everybody is right around 150 and taller, so you don't need all of those numbers. So rather than create this huge graph, we've created what's called a break there. And so this first section is just from 0 to 100, and then now we start counting by 10s or counting by 20s. Same thing here. That allows us to have our graph relatively centered, but still include all the key data and be spread out so we can see it. So yeah, I mean, I sort of see Jose's point. You don't want to have all those numbers in there. It's easier to see the data if the graph doesn't include the origin, which ours really doesn't. And Sunita says it's too small. And man, these people are all over the place. If we're supposed to be using the data to check if the coaster is safe for really tall people, the graph has to have room to graph the tall people. And I'd say, yeah, well, that's true also. Absolutely true. You want to be able to see, because we're trying to figure out if it's safe for everyone, which is really a way of saying, is it safe for the tallest people that might go on it? We know short people are going to have no trouble at all. Medium, average size, probably no problem either. But when you get those really tall basketball players, not very common, but still, they may want to go on a roller coaster too. So you don't want to have your graph too small, and you don't want to have it too big. We got to include enough room to where we could get some of the tallest people and see if the tallest people would likely have a reach that would exceed 200 centimeters. Okay, so let's just come back to my line of best fit for a second here. What this is basically giving you is an ability to predict someone's reach based on their height. So if I said someone was 200 centimeters tall, we would expect from this line of best fit them to have a reach somewhere in the 160 to 170 range. If we had someone who is 220 centimeters tall, okay, so let's put that like this, we would expect that to be somewhere in the 180 to 190 centimeter reach category, in that range. So we want to be able to make our graph So it's scaled properly so we can see everything spread out. We want to determine whether or not it's necessary to have any of these points that are below 100. In this case, it wasn't. And we also want to have it so that we can get to the tallest people and include 200 centimeters on our y-axis, because that's like the danger zone, right? All right, so we've answered all of those. Now, Yao Ming. He was a basketball player out of China who played for the Houston Rockets and I think the Toronto Raptors in the last few years of his career. He was 7 feet 6 inches tall, which is really one of the tallest basketball players. I think Manute Bol was 7'7". I can't think of a taller person who's ever played in the NBA. So, you know, if you're tall people exceeding 7 feet 6 inches, not likely. So it turns out that you don't have to do the conversion here. 7 feet 6 inches is about 228.6 centimeters, round up to 230, but a little bit less than 230. So we can now use our line of best fit to try and determine what his likely reach would be. Now, we can't account for the fact that he might be an outlier with exceedingly long arms, but if we consider everything to be somewhere within the average, plus or minus a few centimeters, we should be able to determine whether or not it's safe for him to ride. And as it turns out, 200, let me thin this out a little bit here, 228 is right around here, which puts Yao Ming right around here, which is between 190 and 200. Yes, that was actually 220. It's probably right around here, and this guy's probably right around there. So I would guesstimate that Yao Ming's height places him very, very close to our danger zone. Now, you might be wondering why I put some of these other points in. Well, while I was doing this, I decided to have students measure me. So that's my measurement. I was the tallest person in the class, and my reach was about 150 centimeters. Then my children, Zoe and Ben, came into the classroom, and they wanted to be measured as well. So I measured them, and I liked having them on the graph because, look, every one of us, we fit very close to our line of best fit. So the blue cluster are only 8th graders. But here I am, the teacher, and here I believe Ben was 5th grade and Zoe was 3rd grade. But they still fall within that trend line. So that just, makes it even more obvious that, it doesn't matter your age. You're shorter when you're younger, you're taller when you're older, and everyone fits on this line of best fit with a little bit of a range, high or low below it. But for the most part, that's pretty strong association. So what do you think? Yao Ming's pretty safe, right? And if Yao Ming, who is 7 feet 6 inches tall, 7 feet 6 inches tall, could most likely ride on this roller coaster without hitting that tunnel ceiling, then chances are most people who ride the roller coaster are going to be safe. So Yao Ming most likely has a reach near 191 to 192 centimeters. And so the conclusions that we can draw from analyzing this data is that the ride is probably safe. Nobody has had any problem up until now, which makes sense, right? Because it's doubtful that anyone taller than Yao Ming has ridden on the roller coaster. So this kind of an activity where you're trying to see how one variable affects another, if there appears to be a strong association between those variables, then you can take surveys of random people and you can plot the information from those surveys into scatter plots, and you can draw conclusions from them like we just did with this activity. Okay, so once again, chapter 7, we're going to get much deeper into this using scatter plots and lines of best fit, and we'll even take it one step further, and we'll take our line of best fit and create a rule for that line of best fit and use that rule to help justify our predictions. All right, so thank you very much. I want you to head over to the homework and make sure You know, when they ask you to create a scatter plot or graph things for your homework, please be neat and orderly with it. Make your graphs complete and copy down the information from the table, just in case you have to make corrections or you feel like you made a mistake. You'll have your work shown. Okay, take care. Bye. Bye.
Hey, feeling good, like I should.